I think it's on. So for A2, we have a, let me just double check if it's on. It should be. Okay, it's on. For A2, there are some leftovers. First of all, we have circular motion that we have not yet talked about. And besides for circular motion, there are some particular type of forces that we should add up to, right? For example, the drag force. So today we're going to talk about the leftover forces first. Let's start from here. So springs. Of course, whenever we look at this word spring, we're going to know what type of forces that we're going to discuss. Elastic force, right? Elastic force. And in NYP, what law did we learn about that is related to spring? Hooke's law, right? Anybody still remember what Hooke's law states?
That equals to negative kx.
Right, that the force applied to a spring is proportional to the extension of the spring, right? So that is Hooke's law. So for springs, the extension of the spring, which obeys Hooke's law, is directly proportional to the extending tension. The extending tension here is the so-called the force applied, or in this case, in DP, we're more focusing on the force within the spring itself, which we call it restoring force. So let's think about this scenario where a mass M attached to the end of the spring exerts a downward tension mg on it, and if it is stretched by an amount of x, then if k is the tension required to produce the unit extension, which is the spring constant, then the stretch tension is also kx. Okay, and so that the mg equal to kx. Basically, let me show you a spring gauge here. What is happening is we have, let's say, spring gauge, and we have some hook weights. Alright, let me put it into the front so you guys can see it. This is a spring gauge. A spring gauge is a device that can be used to measure how large the force is being applied. For example, if I put a hook weight on it, can you read what is the force exerting on this spring gauge?
0.5.
0.5. Okay, why is it just 0.5? Now look at this mass. It's 50 grams, right? So 50 grams is about 0.05 kilogram times the acceleration of free fall, or the gravitational field strength, roughly 10. Then you're going to get roughly 0.5, right? So like that. And we know that this little weight, hook weight, is not falling because the spring provided an upward force to balance its weight, right? Thus, this equation here, mg is the weight of the object, and the kx is the force provided by the spring. Make sense here? Okay. If I keep adding it, right, it's another 50 gram. So can you predict what the reading of this spring is going to be? 1 Newton. Okay, let's see if it's going to be 1.
1.
Okay. So, right, 1. Okay. So that's how it works. Basically, but look at it. When you read it, you have to make sure everything is in stationary, right? What if I move around, like do this? Can you read it? No. First of all, you cannot read it. And second of all, it has acceleration, right? It has acceleration. So it's not in a balance. The force provided by the spring is not going to equal to the weight, only until it is at stationary or moving under constant speed. Like I slowly move it. But if I move it fast, like that, it's not going to be 1 Newton. right? Okay. All right, let's move on. So this is a spring diagram here, right? Basically, it's the similar thing that you hand a spring here, and then you hand a weight here. The spring is going to be extended, right? This is the original length. If I open this, can I open it? Yeah, son. Good job. So you put a hook on it, and then it will be stretched to a certain amount, and this x is called the extension. And here, this graph is the restoring force provided by the spring, versus the extension of the spring, not the length of the spring. Okay, it is the extension of the spring. Now, Thomas, what can you tell from this graph? Proportional. If you double the x, if you double the extension, then
the force is doubled.
the restoring force would also be doubled. Okay, that is Hooke's law. Alright, so this figure 16 shows the variation in the tension produced by the spring against the extension of the spring. When the graph is a straight line through the origin, then we say that FH, which is the restoring force, is proportional to x or versus x, and then the tension is directly proportional to the extension. Okay, the tension is the FH here. This is known as Hooke's law because Robert Hooke is thought to be the first person to formulate this relationship. All right. So you just need to know this is Hooke's law when the extension is directly proportional to the restoring force or the tension force within the spring. Questions? Yeah. This x is extension, which means it is the current length minus the original length of the spring. It could also be negative when you compress a spring. Then your current length is shorter than the original length. Then x is negative. Does that make sense? Okay. It could be a negative thing. If it's negative, you just need to extend it from this side. That indicates here. So let's look at this here. This law can be written as FH equal to negative Kx, where K is the constant of the proportionality, also known as spring constant, which you already know from MYP. And the unit for K is Newton per meter. All right, so here, let's look at this. The negative sign in FH equal to negative Kx reminds you that the force that the spring exerts is in the opposite direction to the extension. What does that mean? That means if I look closely, if I stretch this downward, what is the direction of the extension?
Upward.
Direction of the extension.
Down.
Downward, because displacement is going down, right? How about the force provided by the spring?
Upward.
Upward, right? Because it will try to prevent this object from falling, the spring must provide an upward force within to support this thing, right? So the direction of the spring force, the tension is upward, while the extension is going down, which means the force is in the opposite direction to the displacement. It's in the opposite direction to the x, right? That's why there is a negative sign. Because this FH is describing the tension force provided by the spring, not the external applied force. Okay? Any other questions? So far so good? Alright, let's move on. So this is the Hooke's law, which is FH equal to negative Kx. Right? Whenever you're asking what is Hooke's law, if you write this equation, don't forget to explain what each letter means. Alright? Can I move on? Now, let's think about what if there are several springs, right? We have 2 springs or 3 springs. Now, in this case, we're going to combining the springs. What is this way of combination? It's called in series, just like in a circuit. Last semester we learned how we combine resistor. This semester we can learn how do we combine springs. So let me get one more spring here.
I didn't get that. Could you try again?
Siri.
All right. So if we're going to connect them in series, basically I need to hang this on the top of another one, right? What's going to happen here if that's the case? What's the reading upward? 0.4. What about the reading below on the second scale?
0.
0. Which makes sense because this thing has nothing down below here to drag it, right? But this thing needs to support it. Its weight is dragging the first spring downward, right? Now, let's hand this thing on top of this one here. Think about this. What would be the reading on this one? And what would be the reading on this one? Right now, this is 0.4. Okay. Let's see if it's what we predicted. What's the reading? First of all, below it, what's the reading? And upward? 0.9. Okay. This is 0.4.
是你刚才没调的吗？有一点点。
哦，它有那个 systematic error， 对吧？没有调零。OK， 现在再来看一下是0了啊。现在是 0.5 了吗？
差不多。
差不多，不过挺好。Okay. Does this result make sense to you guys? The bottom one is 0.5 almost. The top one is 0.9. If I remove this from the hook, what's the reading on the top one? 0.4. Okay. Questions? All right. So now 2 identical springs, P and Q, both spring constant, both have the same spring constant K, are connected in series, and a weight mg is held on the bottom of Q. Each spring has the same extension, and therefore extended by each extends by x equal to mg divided by k. The total extension for the pair of the springs is 2mg over k. Hooke's law for the spring is thus mg equal to k prime 2mg divided by k. Questions? What I just showed you is in reality, but in theory or in ideal situation, we don't consider these springs, we don't consider it has any mass. So those are massless springs, which means the only force acting on both of the spring is purely this mg. And then the force together provided by the 2 springs should be also just equal to mg. Does that make sense? Okay. But each of the spring, because they have the same extension, same spring constant. Now, as we have already know from yesterday, we do a demo when we are connecting 2 things, right? You apply force from both sides. The forces are equal. Are they equal? Okay. If we tie a strain here, like this one here.
一边挪的 x， 另外一边挪的 x， 两边都是以同一个 coefficient 因为总共的 extension 不一样。
哎，来帮帮我。
哦，好的。
Is this still the same reading? No. 读数不一样吗？
差不多，差不多，也1.5。
啊 Okay. Which means the forces, the tension within the strain should also be the same. Does that make sense? Okay. So that means this here, if this spring has a tension of mg, this spring should also have a tension of mg, right? Okay, so in total, the total displacement is 2x. So the new one is mg, which is the force, equal to k, the new k, times the new displacement. New displacement is 2x, right? 2x. So you're finding this k prime. K prime should equal to mg divided by 2x. Okay, so let's move on. If that's the case, then the k prime is just becoming half of the original one. Half of the original one. So where k prime is the new spring constant for both spring acting together, and this leads to k prime equal to k over 2. If they have a different spring constant, they follow this equation. Does this format remind you of anything you learned last semester? Resistor combined in parallel. So here's the difference, right? Combining spring in series is similar to combining resistors in parallel. That's our conclusion here. That's our conclusion here. If that's the case, what if we combine springs in parallel? What can you think of?
直接加 k prime equals k1 plus k2 plus k top.
If that's the case, that means 我要是有细线就好了。我如果有细线的话，我可以这样子用这个吧。If I do it in parallel, basically what happens is those two together will support this thing, right? So the weight will be shared by two springs. Similarly, like if, how do I say? Like, 来两个大汉，就你们两个吧，来啊。我们来做一个演示，你站这边，你站这边，好。If there's only one person, right? 你试着把我拉我这手把我拉起来，
拉起来。
啊，是不是有点困难，对吧？好，两个把他一起来拉，把我拉起来，So basically, thank you very much. So basically, when you have two springs, right, to hang on one thing, you're sharing the weight by half, right? It's easier for them to lift me up. So basically, if this thing needs 10 Newton to lift it up, then each spring can only apply 5 Newton. Does it make sense? So if we move on, when when two springs are combined in parallel, the weight is being shared between them. So to see this, remember that the force downward is only mg, and when the spring are in equilibrium, the total force upward should also be mg. Then each of the spring provides exactly mg over 2. Does that make sense? So each spring will only contribute to 1/2 of this force. That is mg over 2 for each spring. Sorry. And so that if there is going to be different spring constant, the equivalent spring constant for parallel is going to be just to plus them together simply. Just to plus them together. Actually, think of it like this. When you combine two springs in parallel, so what if you put this together, right? Together with it. You're basically making it thicker. If it's thicker, it's more difficult to stretch it, right? It's different. So that is the reason why we plus the constant together. And if you look previously from last slides, if you connect them in series, basically overall it becomes thinner, because originally it's this thickness with this length, but now you extend the length by twice. The ratio between the thickness and the length has been, the ratio between the thickness and to the length has been decreased because length is increased. So technically you can think of this as thinner. So it becomes softer or weaker. So your equivalent spring constant will decrease. Does that make sense? Questions? Okay. Move on 了，可以吗？好。Now buoyancy. We have already learned about buoyancy, right? Anybody still remember the formula for buoyancy?
Density
Rho GV. What is rho? The density of the object? Of the fluid, of the liquid. G is gravitational field constant. What about V?
The volume of the object.
The volume of the object? The volume of the liquid displaced by the object, right? Okay, so buoyancy, the buoyancy force experienced by an object is equal to the weight of the fluid displaced. Interesting. So that means you display how much water, the weight of the water is equal to the buoyancy that this object experienced. Because again, we have already told you it's rho liquid times G times V displaced, right? What is rho times V displaced? This displaced water, right, or liquid. So this basically is the mass of the liquid that's being displaced, times G, that's the weight of the liquid that's being displaced. Does that make sense? So buoyancy Fb acting on the body due to the displacement of the fluid as given by this equation, Fb equal to rho GV, where rho is the density of the fluid, V is the volume of the fluid displaced, and G is the gravitational field strength. Okay, so here I prepared this amount of water. Can you read the volume for me? 450。数一下啊，少一点，因为我们要读这个凹页面最下面，对不对？我再加一点水吧。再去帮我接点水来。Okay, so let's do an experiment and see how much buoyancy those things experience here. Okay. 多加点，让它明显点啊，我们多加几个。好，6个差不多。人呢？稍微加一点，加到450。多了。哎呀，好烦呀！还是多了。
多了一个。
就熬夜量好像地理一样。
Okay. Right now, what's the force?
300. Oh, the 3.
大家看好啊，看有没有读错？
看不到，后面3。
其实算应该是吧。
2.98。
2.9，好。Now, is the reading changing? What's the reading now? What's the reading now? 2.4? Okay, read the volume right now. More than 500 or just about 500? Just about 500. 好，我们来记录一下。现在又变回了2.9，对不对？来，你先帮我 hold 着，我要累死了。对，我们先记录一下数据。So before the spring gauge, the force equal to 2.9，是吗？What's the reading right now?
现在是
2.4. 2.4. What's the volume initially? Volume initially is 450 milliliter. What's the volume right now? 500 milliliter. Thank you very much. 你可以休息了。帮我拿几张纸来吸一下。Okay, so according to this data, let's find out what's the buoyancy that this thing experienced under the water. 0.5. Buoyancy FB equal to F1 minus F2, right? Which is 0.5 Newton. Now let's calculate the water being displaced. The water has been displaced how much? 50 milliliter. This much of water, how much is its weight? Okay, let's think about what's the density of the water? 1 gram per meter cube or per milliliter, right? So, which means the mass of 15 milliliter water should have how many grams? 50 grams. 50 grams equal to 0.05 kilogram. If you times 10, the weight of the water is
0.5.
0.5 Newton. Isn't it exactly the same as the buoyancy? OK 吗？哎呀，今天这个应该用那个 video record 的。哎，真的是。
我是哪个老师那么坏？
这不好说吧？你这是在给我设陷阱。Okay, let's move on. All right, now let's look at terminal velocity. So terminal velocity is the velocity reached when forces on an accelerated object balanced and it stopped accelerating. Let's look at a skydiving example on the Earth. So skydiving on Earth, what happens to skydivers after he jumps? After he jumps, gravity is the only force acting on the skydiver immediately after the jump. Because immediately after the jump, he has not fallen yet. And there is no relative motion between the skydiver and the air. So there's no air resistance yet at that moment. Immediately, the only force acting on the skydiver is just gravity. But as the skydiver keeps falling downward, its velocity is increasing. It's moving through air. Let's see this one more time. 1, 2, 3, go. As velocity increases, so does the air resistance. But air resistance cannot increase infinitively, right? Because if air resistance to the point that is greater than the weight, then eventually the skydiver will move upward. And that's not going to happen in our real life. We know that, right? So when would air resistance stop increase? Once it equals to the weight of the skydiver. So once it equals to the weight of the skydiver, right, the air resistance balances the weight, it stops accelerating, which means speed no longer increase, and thus air resistance no longer increase as well. Then it reaches its terminal velocity. If skydiver opens up his parachute, then air resistance will increase dramatically, but weight stays the same. That's how the skydiver slows down its speed. As it slows down, what would happen to air resistance?
Decrease.
Air resistance would gradually decrease until it reaches a new, much slower terminal velocity. Does that make sense? Questions in this process? So far, so good. We walked through in grade 9. Alright? Okay. And then touch down to the ground. Okay. Let's look at another example. Skydiving on the moon. If you skydive on the moon, what would happen? What would you expect the velocity time graph to be? If you're going to skydiving on the moon, what would the velocity time graph to be? Jessica, what do you think?
But on the moon, isn't it in the straight?
Yes. It's in outer space, but not necessarily in the space. If we're talking about in the space, we're talking about zero gravity. But on the moon, there is gravity. The moon will attract you downward. But what's the difference on skydiving on the Earth and skydiving on the moon?
Less gravity.
Okay, less gravity, sure. What other differences?
Less friction.
Less air resistance. No air resistance.
There is.
Is there air resistance or not?
I'm not sure. I don't know.
Is there air on the moon? If there's no air on the moon, how does it have air resistance?
I don't know, maybe something else. Some kind of gas.
Is there any gases on the moon?
No.
No, there's no gases. There's no atmosphere on the moon. So, no air resistance, free fall. Free fall on the moon. And because it's free falling. Okay? It's free falling. Do you understand the differences now? On the moon, there's no way you can reach terminal velocity because there's just no atmosphere. There's no air resistance for you to help you reach the terminal velocity. You're just going to keep accelerating forever and ever and ever. Okay. Questions? No questions, move on. Viscous drag. So, the third force is the drag force. Viscous drag is defined as the frictional force between an object and the fluid which opposes the motion between the object and the fluid. Now, that gives us the Stokes law. So, the Stokes law states that in this 1851, right, we have this scientist, George Stokes, derived the theory for the drag force, which called more properly the viscous force, acting on the small sphere that is moving through a viscous fluid. Do you know the word viscous? What does it mean? Viscous in Chinese means 粘稠的. So viscosity is 粘度. It is a property described by a fluid, how thick, how sticky it is. For example, water and oil, which one is more viscous? Oil, right? Water, alcohol and honey, which one is more viscous? Honey, right? Because it's more difficult to flow through those fluids. It's more viscous. Okay. So a viscous fluid with high viscosity, such as concentrated sugar solution or an engine oil, has high resistance to deformation. It will pour slowly. So you pour water, you see, you can pour water pretty quickly. But if you pour honey or oil, you can tell that it's kind of like stick together and you don't pull it that fast. Does that make sense? Okay. So a low viscosity liquid such as water has low resistance to deformation and pours quickly with little drag. Alright. So, what is Stokes' law? Now, Stokes' law has the following assumptions. He assumes that the flow is laminar, so that the layer in the fluid flow smoothly pass each other without mixing. The alternative format is turbulent flow, where the layers mix and the whole of the fluid swirls about a random manner, in a random manner. So here, look at this. This side is kind of like everything is in order and they pass through each other smoothly, right? This is what we call a laminar flow. Here, in this, you see those swirls, right? Everything appears to be more chaos. This is what we call turbulent flow. Turbulent flow. 但是我估计我在希沃上写的这些笔记不会被 record 下来，所以你们之后 watch 这个 recording 的时候可能会有一些 information missed out。
考了 laminar
Okay. 这个不考。You just need to know this is laminar, this is turbulent. That's all. And that the moving particles are spheres with smooth surface, and that the fluid is homogeneous. Homogeneous means it is uniform in composition. Okay. 5 minutes break.
这个 stop small 讲的是那个啥？
让我来不了，
Stop recording.
那就 stop 吧。